All right, hello there, everyone. This is Professor Masinski. I'm covering my course notes from today, January 13th. It's the first class in CIS352. So I talked over how to define values. So here I've got a top-level value. We won't usually do this in Racket. It's sort of like a global variable, let's say. It's at the module level in this case. We're not typically going to want to do this, but it's an interesting place to start because if I hit run now, I can see in the REPL that I can now type foo and it evaluates to 42. Okay, so then we discussed how to define functions in Racket. So in Racket, basically everything is surrounded between parentheses. So the define form, when we use it to define functions, we're going to have parentheses, and then the name of the function is the first thing. Here it's identity, and then x is the first formal parameter. And we're using that value x. Now, the comment here says something important, which is that Racket is expression-based, and so expressions evaluate to values. Values are the primitive things that the computer represents, right? So a value is something like 42, or the string hello. These are both syntactic values. The computer immediately can interpret them as primitive values, right? In comparison, we might have something like plus 20, 25. Now this is a computation. It's an expression. In this case, it's function application of plus to the arguments 20 and 25. Now these things are different, and we're not exactly prepared how to discuss formally why an expression is different than a value at this point in the course, but it's intuitively a concept that we want to start building now. And so intuitively, a value is the result of some computation, something that can be returned by a function, right? That might be how you could classify whether something is a value. In this case, I'm taking the function identity and I'm applying it to 20. Notice how in Dr. Racket, if I hover over identity, I can see this little back pointer, this little arrow right here. That's showing me the provenance of that function name, identity, right? So that's kind of an interesting concept. I can see when I hover over usages of things, where do they come from? So for example, plus and times, those are things that are imported from the Racket language. By virtue of using #lang Racket, I get like a built-in environment and a set of global variables that includes the basic definitions for numbers and things like that. But then here I'm extending it with a function of two arguments, bar and xy, and the evaluation of bar xy is plus of x times x, quantity 2 times y. So I'm adding those things together, and then that's the result, and I could call that, for example. I did that during class. And then the last thing I did was I said, here's how we would define the factorial function. I wrote it on the board in class by using, cases in mathematics, but it translates here into an if statement, right? So we branch. The base case is that fac of 0 is 1. And then the inductive case, or the recursive case, is that if we've got any x greater than 0, we take x times factorial of whatever x minus 1 is. And that's the result of the factorial function. And this is a very primitive recursive function that we would generally use over the numbers. There are some downsides with using it to teach recursion that we might get into eventually, but it's a simple one that we would code up, and much of the class has seen Haskell before, so this will seem somewhat familiar in that regard. We talked about the fact that Racket is what's called a call by value language, meaning that a function in the language, every function in the language, operates to first evaluate its arguments down to values. Remember, values are the primitive things that the programming language is representing, the primitive notion of sort of an object or data in the language at its runtime is a value, right? So something like a string or a list or something that's the result of a computation is a value, right? And that's distinct from a function call, for example, or a piece of syntax that's something like an application or another form. And so we're going to get into seeing what is that distinction as we move throughout the course. But to illustrate it, the case that I tried to make to the class, and this is something I always talk about on the first day of my class, is basically how do we show to ourselves that if, which is this form that allows me to branch, how do I show myself that it's not a function, right? Because it's not a function, it has what's called a non-standard evaluation order. Well, the first thing to do is to recognize, and this is just something you have to know about Racket, that Racket is a call by value language. And so if you were to write, let's say you were to wrap if and make it a function by using this little definition, if v, which takes a guard, true, and false branch. All of those things are going to be arguments. All right, so that's going to be the sort of way we're going to implement if v. There are other ways you might do it that could get it correct. And so, you know, this is a little bit artificial, but let's say we did it this way because I think it really illustrates the key point. Well, the issue then is that because call by value forces the application of this function to evaluate all of the arguments, we have to evaluate this, which gets true, this, which is the string you see here, but then this call to loop, which we would not do in the second definition on line 38. We still, because it's call by value and we're calling this function if v, it's the last argument of if v. And so we have to reduce this to a value, but we can't do that because this is an infinite loop, right? It's a zero arity function that then calls itself in its body. And so once you call loop, you never get out. It's like a black hole. You just call loop and then that calls loop and then that calls loop forever and ever. And that's all you can do. But the regular form of if we comment out this call right here, this totally avoids the issue because we see true, and then if only evaluates either the true branch or the false branch once it knows whether the guard is true or false. And so that's different than if it were a function where you would have to evaluate, you know, the first argument, the second, the third, and so on in order until you were done, and then you would evaluate the body, right? And that's a key concept to get across, is that notion of call by value. Just to give you a few more thoughts about where to go after this, if you kind of want to build on today's class, we might define the Fibonacci function. So we might say fib of n here is, we can use a few things. We're going to say if n is equal to 0, then let's say that that's 1. Otherwise, if n is equal to 1, we'll say that's 1. And otherwise, here we're going to say this is going to be plus a fib of minus n1, and then fib of minus n2. And this will allow us to calculate the Fibonacci number n, the nth Fibonacci number. And so if I say fib of 15, I can see it's 987. That one I don't remember myself. Let's look at the fifth. Okay, that's 8. So that's one I actually remember. Now, this is a little bit ugly. And the reason it's a little bit ugly is mostly just stylistic. And it's that the code goes across the page the further we get. So we could replace this. So let's take this and we'll comment out this whole thing. This is how I do a comment of a whole S expression in Racket. Notice this little thing that's highlighted here is the whole if. Well, here's an issue. If I want to comment out just this line, well, then now I'm suddenly broken the expression. And that's really ugly, particularly because if I want to comment out the whole thing, well, then now I got the parentheses here that are unclosed, right? So when I'm working in Racket, I'm usually going to want to work on a per expression basis. And so I can comment out this whole S expression by doing pound semicolon. That's a very helpful tip. So let's replace it. And we're going to say cond, which is a different if type construct that allows us to have multi sort of case handling by saying if this first thing happens, so if we see equal of n and 0, then it's going to be 1. Otherwise, we're going to check the next case. This is going to be 1 as well. And then we're going to have else, which is going to be a final case. And that's just kind of a magic thing. Else is the last case you can add, and that will catch everything else. We're going to say it's going to be plus of fib minus n1 and fib minus n2. Okay, and now similarly, ooh, I just accidentally added one too many parens here. Okay, so now I can hit run. And once I've done this, maybe I want to actually just throw away that old implementation. And so I might highlight that whole thing and delete it. And then I need to hit run again. And then let's do fib, let's say 10. And I see it's 89. That one looks correct to me as well. And then there's going to be an issue, which is that if I call fib of 100, for example, it's actually going to be quite slow. And it's slow for kind of a silly asymptotic reason. The reason it's very slow is that I'm actually going to be repeating a whole bunch of work the way that I've implemented this algorithm as is. It's actually exponential time. In fact, to be specific about it, the time is 2 to the phi, where phi is the golden ratio. That's not surprising, right? Because this is the Fibonacci calculation. But because I'm calling fib twice, I'm going to be redoing a massive amount of computation, and it gives the algorithm this kind of inherently exponential type flavor. But actually, this is sort of silly because it turns out there's a way better way of calculating the Fibonacci number, or at least the nth Fibonacci number. And what you do is you basically build up a table. And the general name for this technique is called dynamic programming, or memoization might be a specific way of doing it. What you're doing in memoization is that you're building out a table of the nth Fibonacci number. And you start out by having a table that consists of 0 and 1, and you initialize those both to 1. And then to build the sort of next cell in the table, you look at the previous two and you sort of pass it along, right? You take the previous two, you add them together, that's the next cell, and then you work on the next cell after that. So that's an intuitive way of doing this in a better manner. But that appeals to the notion of a table and a list or something like that, some sort of data structure for representing it. So instead, it turns out that in this specific case, you can do this in a much easier manner, which is to recognize that actually you're only looking, that table is really, you only need the most recent two Fibonacci numbers if you're only going to calculate the nth Fibonacci number, right? And so what you can do is you can re-implement the function in this way. You can say, I'm going to call it fib memo, and this is going to be in 0 and in 1. And in 0 will hold the sort of the nth Fibonacci number. In 1 will always hold the n plus 1th Fibonacci number. And so we're going to say here, if, and then we're going to call it n, is going to be our, maybe let's rename it to be A0, because A stands for accumulator. So here, let's say cons equal n0. Then we're going to hand back A0. Otherwise, equal n1, then we're going to hand back A1. Else, let's say fib memo of n, and we're going to say A1 here, and this is going to be A0 plus A1 in this call to fib memo. And I made a mistake here. This needs to be n minus 1. And now I can define optimized fib of n to be fib memo of n and 1 and 1. Okay, so now let's try it. Optimized fib of 0 is 1. Optimized fib of 1 is 1. Optimized fib of 2 is 2. Optimized fib of 3 is 3. Optimized fib of 4 is 5, as expected. And next, we should expect to see 8, right? Okay, good. But now here's the cool thing. So if I do fib of 20, that's a little bit doable. What if I do fib of 30? Well, it's a little bit slower, and fib of 40 is quite slow. And this is, remember, the old exponential style of fib. Formally, I would say this is big O of n, 2 to the n. I believe it's really phi to the n, as I was arguing earlier. But the constant factors don't matter in big O, right? So here, in fib memo, or in optimized fib, I can do 40 much faster. I can do 100 very fast. I can do 1,000 really fast. That's because in optimized fib, I'm using this memoized implementation of it, right? And so you're able to get a lot of power by using tricks like that, even without having to leverage any more of a high performance data structure. And this is a little bit of a trick that we'll see a little bit later on in the course. It's kind of written in a tail recursive style, and we'll study algorithms that sort of affect that style. There's a good reason to believe that programming in this manner, it has a lot of overlapping with traditional loops that we might see in imperative programs. And so that's just a little bit of, exposition, me kind of waxing poetic on top of the topics from today's class, but hopefully this was insightful if you're learning Racket as you go. So thanks for tuning in. I'll be back, next time with more elaboration on top of the course notes. All right, so see you later, everyone.